Welcome to Avian Analytics final presentation. The people you will hear speaking today and the team members are Abhijay, Bill, Caitlin, and myself. Our team leader is William Shamblin, and our graduate mentor is Kelsey Lieberman. The goal of this project is to end up with a working device that will use a low-powered single-board computer with a camera to detect, classify, and record species of birds in a natural setting, utilizing a fast and accurate machine learning model, all the while uploading the collected data to a central repository. Motivation being that this data could be used as an excellent source of information for biologists tracking species migration patterns, and additionally, the development process and final working device can be applicable to other fields. To give you all a breakdown of how we've spent the last summer, this is an overview of our progress. In the first 4 weeks, we set up and familiarized ourselves with the Nano, the virtual environment, the cluster, and other tools. We followed an object detection walkthrough called PETS to train a model. Using the knowledge we got from this walkthrough, we created custom TF records for the Cub 200 dataset, trained models on this dataset, and then moved models over to the Nano. In weeks 5 and 6, we followed a similar process to what we did on the Cub 200 dataset with the iNaturalist 2017 dataset. Once the models were trained on this dataset, we moved these over to the Nano, worked on converting to TF, TRT, and TF Lite formats, which are more compatible and more efficient on the Nano, and began training the You Only Look Once, or YOLO models. Weeks 7 through present, we finished training the YOLO models, moved them over to the Nano, converted them to TF, TRT, and TF Lite formats. From here, we implemented object tracking and counting. We increased the speed of inference measured in frames per second, and presently we are working on finishing up our scripts, finalizing the documentation of our process, and pushing all of this into a JIT repository. To give you a better idea and clearer visual, here is the single board computer we are working with, complete with a camera attachment and a Coral USB accelerator. The Jetson Nano allows users to run multiple neural networks in parallel for applications like image classification, object detection, segmentation, and speech processing. We use a small camera that's attached to record and capture birds. The Coral USB accelerator adds an edge TPU coprocessor to the system, which enables high-speed machine learning inference.
So the image data sets we've been using for training are the Caltech UCSD Birds 200, which is 200 bird species, mostly North American. And this is a small data set of only 6,000 images, and it has like the information we need, like the bounding box, and its attributes. This data set we mostly used as our to get our feet wet to understand what we're working with. So mostly we have now been working with the iNaturalist 2017 data set, which represents 5,089 species, and of them 964 species are birds. And that alone is 235,000 images, which is a much larger and more comprehensive data set. And although this data set comes with its own JSON files, we needed to do a lot of work to fix them up. We had to deal with missing images, bad bounding boxes, is crowd being hardwired to 0, and multiple annotations being annotated at a super category level. And we also have about 17% of the images having more than one bird in it, which means that we needed to change the TF record generator scripts to take that into account to make sure that the model doesn't get confused. We are taking the pre-trained models and retraining them to identify birds instead. So each model has its own config files that corresponds to defining the architecture of the model and its training process. So for each So for each model, we have to have a new config file for it. And these are some examples of pieces of our config files for one model in particular.
So on the left here, you can see a number of different models that we've trained throughout the course of the summer. Most of these models we've taken off of TensorFlow Git repo from their model Zoom, which provides us with the model itself as well as the config files that we use for training. So after we spent a few or so weeks running these models, we decided to start looking into optimization, because one of the main challenges in object detection on single board computers is the size of these models and being able to fit them on this small device in order to get it running at a good frame rate. So here we have two optimizations that are running on the same model. On the left, we have TF Lite, and on the right, we have TF TRT. So it's important to say that there are three main optimizations that we were looking at: TF TRT, TensorRT, and TF Lite. So the TensorFlow itself takes a lot of time to and a lot of RAM on the Jetson Nano. So in order to fix that, we have the first optimization, TF-TRT, which is kind of a hybrid between TensorFlow and TensorRT. And we also have TF Lite, which is specifically designed for the Google Coral and its hardware. As you can see on the left, the average inference time on the Coral is around 25 milliseconds, while on the right, TensorFlow TRT is around 360 milliseconds. Based on this, we expect TensorRT itself to be somewhere in between these two. So the reason that TF Lite is so fast, especially on the Google Coral, is that a lot of the weights and values in these models are normally stored as floating point. So the TF Lite API converts these floating points into floating point 16, and as well as 8-bit integers. And this allows for the model size to be reduced by up to 75%, and it significantly increases the inference with minimal accuracy loss. Unfortunately, one of the limitations is that not all models can be quantized. This stems from different aspects of the config file. You have to have specific nodes starting off in the training to allow the model to be quantized without losing too much accuracy. And based on our previous results between TF Lite, TensorRT, and TF TRT, we were hoping to aim for TF Lite as our optimization for whatever final model we decided.
One of the models that we were looking at through our training process was the SSD Inception v2. SSD stands for single shot multi-box detector, and it is defined by dividing up each image into a number of little grid cells, and it is able to generate bounding boxes based off of these grid cells and then do classification as well, all in one look of the image. In the graphs on the right, there's a lot of them, but the main takeaway is that it was fairly accurate compared to some of the other models that we were training. Usually, the higher the graph goes would be preferred. The top set of graphs measure MAP, which stands for mean average precision. Precision in this case measures, given a picture of a bird, what is the chance that the model is going to identify the bird correctly. On the bottom set of graphs, we have recall graphs. Recall is a measure of accuracy per category. So given a category of birds, say like 50 bird images, how many of those were identified correctly? And we found that the SSD Inception v2 had both very good precision and recall compared to other models. The only problem is it was very, very large. And it was so large that we couldn't quantize the model, because when we tried to put it through the compiler, it would run out of memory while it was quantizing it. So in that case, we've been looking toward the YOLO models, which are similar in how they detect birds, in the sense that they only take one look at the image to detect multiple birds. But the YOLO models, and especially the tiny version of the YOLO models, are much smaller. So we're able to get these models converted to the TF-Lite formats to run on the Google Coral, as well as other different formats with very fast inferencing time and good enough MAP to be usable. And the biggest benefit is being much smaller than the Inception V2 that we were working with.
So part of our project is not just looking at birds and being able to detect and find their bounding boxes, but also being able to count them. And part of being able to count how many birds we found for each species involves tracking, object tracking, and counting. So what we've been using is a centroid tracking algorithm to track the birds as they move across a frame and to count the number of birds identified for each species. The main parts of this algorithm is that makes it work reasonably well with our models is that it first tracks the max disappeared. So how many frames, consecutive frames, the bird must be gone to be considered like actually not there anymore. And this is important because our models don't always catch a bird, whether it's because the bird is not positioned nicely or because the model is just uncertain. The downside of this is that the bird of the same species that immediately comes after another bird of that species has just left, it will recognize that new bird as the original bird. So if you take two pictures of the same cardinal, they're not going to be two cardinals. Another major part of it is keeping track of the minimum number of consecutive frames a bird must be detected to be considered for tracking. And this has given a massive improvement in overcounting because it takes care of the flickering model prediction, like the model for a few seconds think that this is like 3 different other birds. And that is a great help. The main part of this is the updating part, and we first match the current birds we're tracking by species and then by centroid proximity, and then we match it to remaining birds that are pending, which are the birds that haven't made the cut for tracking yet. And of course, we're not just tracking the current birds, we're also tracking the total count and the timestamps for each species found, and we export these to a CSV file. And our main limitations is that the tracking and counting only works as well as the model. So the better the model, the better the tracking and counting. And also, despite what we've done to reduce overcounting, it does occur at times, but it is mitigated a bit by the undercounting that happens because the model isn't quite accurate enough for some birds.
So here you can see our final inferencing demo that's implementing the YOLO v4 Tiny, as well as the centroid tracking algorithm. So each, on the left is the model running on a stock video of birds, and on the right is the live webcam. So each individual demo switches between a view of every frame inferenced versus every 4th or 5th frame inferenced. The main goal, or the main point of this, is to exemplify one, our I guess potential inferencing capabilities, which would be the real-time every frame inferenced. But ideally, our goal is not to produce a labeled video. It is more just to provide researchers with data of birds passing by and just their population size, ideally. So because of that, every fourth or fifth frame is more ideal, as it lessens the amount of buffering frames in the camera and speeds up the time overall. So our final goal here was that we were able to achieve around 6 to 7 frames per second on the Jetson Nano with this YOLO V4 Tiny. And the source code for this whole training process and inferencing scripts have all been added to GitLab so that this whole, everything can be reproduced and ideally applied to new models that may come out.
So looking ahead, this field is moving very, very fast. Just recently, the object detection API that we were working with was updated to work with TensorFlow 2. We were currently using TensorFlow 1. So within the project, advances are always being made. And this can apply to different optimization techniques that come out and can be applied as well. In addition, these models can be trained on different types of data sets, ranging from different kinds of animals to different data sets of the same type of species. And I think overall, object detection is just a very sort of promising field that is making waves in sort of different areas like traffic and self-driving cars. And so the work here can easily be, the work and principles applied here can easily be applied into more just a wide range of fields. So there is a lot that can be expanded upon with this project. It was a pleasure to work with my teammates this summer to try to put all of this together, and I hope you enjoyed this presentation.